morning to Associate Professor Ray Dugstein and Mr. Christopher Fields. My name is Kai. I'm present here today to present my research project entitled Microfluidic Fabrication of Emulsions using T-junction microchannel. Now, before commencing the presentation, I would first like to express my sincerest gratitude to the following people. I would like to thank you, Professor Ray, for your constant support and your persistent help on putting me in the right direction upon completion of this project. Thank you, not forgetting Mr. Chris, for your constant assist by making the T-junction devices that were used in the experiment, and not forgetting your constant aiding in helping me completing this project. Ms. Marta for your necessary lab safety conduction, and not forgetting lastly Ms. Davina, also known as my research partner, for her superb help and teamwork throughout the completion of this project. Now right here, we have a presentation outline of today's, we have an outline of today's presentation. I'll be first touching on the introduction, and I'll be talking about the project's aim and certain literature reviews about the project, followed by describing the materials used in this experiment, and I'll be talking about the methods on the image analysis for my results. And then I'll be talking about the results and discussion obtained from the experiment, and finally concluding today's presentation, and I'll be talking about limitations and recommendations about my research. Now, first of all, I'll first like to define what an emulsion is. Emulsion is simply a mixture of two or more liquids that are immiscible. Emulsions are used in technologies that are from food industries such as ice cream manufacturing to consumer products industries such as shampoo production. In this research project, we emphasize on the formation of droplet in a water and oil emulsion system for large-scale stability studies using microfluidic T-junction devices. A sketch of the T-junction device will be shown on the next slide, on the next few slides, so bear with me for a second. The aim of this project was to validate the scaling equation right here, and it was the main focus of our experiment, and this was to predict the size of droplet generated in microfluidic T-junction device in relation to generation of droplets under two specific regimes, which are the squeezing and dripping regime. I'll be shortly describing what these regimes, the mechanism of these regimes are, and be showing the parameters of the scaling equation. Besides that, we also studied the effect of changes of viscosity of the dispersed phase liquid on the droplet size generated under the squeezing regime only. So right here we have the scaling law along with the parameters you can see here. So it is very important to note that the scaling equation is independent of the interfacial tension between the two liquids used and also the viscosity of the liquid. So with this scaling equation, we have a guideline of expected droplet size generated, of course with a desired flow rate of either the continuous phase or the dispersed phase liquid used. Right here we have the sketch of the T-junction microchannel. Now as you can see, the two phases were joined at a right angle, and the main channel carrying the continuous phase liquid, whereas the orthogonal channel will carry the liquid that will be dispersed. And basically I'll be talking about the mechanism of droplet breakup soon. So this T-junction microchannel was beforehand fabricated with a thin film of polydimethylsiloxane, also known as PDMS. This was to facilitate the observation of the oil and water system in the microchannel, either visually or under the microscope. Now, inside the microchannel, there are three forces that play a vital role in the mechanism, in the breakup of droplet. So firstly, we have the shear force inside the microchannel exerted by the oil stream on the emerging droplet, followed by a Laplace force inside the droplet. Now, this was due to interfacial tension, and we have growing upstream pressure in the oil phase. Right now I'll be talking about the mechanism of droplet breakup inside the T-junction microchannel. So under the mechanism of squeezing regime, the Laplace force dominates over the cross-flow shear force. Having said that, the pressure upstream of the channel squeezes the neck of the droplet, and the droplet then breaks up as soon as the two liquids intersect at the T-junction right here. So as the droplet travels downstream of the channel, it occupies the entire space of the wall channel, and the cross-flow shear stress exerting upon the droplet right here is low, as the gap between the channel's wall and the droplet is all filled up. So yeah, therefore the cross-flow shear stress is pretty much low for the squeezing regime. And moving on, for under the mechanism of dripping regime, the emerging droplet is not in contact with the channel's wall. It's quite dark here. Anyway, it does not occupy a space. Thus, therefore, the cross-flow shear stress acting upon the emerging droplet traveling downstream, that is definitely higher than the repulse force. It's just a simple mechanism. Moving on, I'll be describing the materials used in our experiment. We have canola oil and millipore water, polyglycerol polyricinoleate, also known as PGPR, which will be used as emulsifier in our experiment, and lastly sucrose. Now PGPR is an emulsifier mainly used in the food industries. This was to minimize the interfacial tension between the oil and water system in our experiment. We use that to create more stable emulsions. And sucrose was added to increase the viscosity of the dispersed phase liquid, which was water. And this is because part of the experiment was to study the relation between effect of viscosity with the droplet size generated. So we prepared 20 weight percentage and 50 weight percentage of sucrose solution for the experiment. Now here are the list of instruments used in the conduct of our experiment. We have two NE1000 single syringe pumps. We use 1 ml thermal syringes connected to the pump, as you can see in this picture here. And then syringes will be connected to our T-junction devices, which will be put under the microscope. We use the Nikon Eclipse TE2000U inverted microscope with twin CCD cameras with a 20 times magnification. So this microscope here will be connected to a computer where we use a program known as the V++ demo program to capture live images of the droplet. So now, in order of obtaining the length of droplets, the two approaches of measurements were used for image analysis. Firstly, for droplet generation under the squeezing regime, we use the direct measurement using V++ demo. As I mentioned previously, we just attach the T-junction device under the microscope and connect to V++ demo. Then we capture live images, and then as soon as we capture live images, we paste the images onto Microsoft Paint. And you can see on the picture on the left, my left here, we just draw a line from one end to another end of the droplet to measure the length, and that will be in pixel measurements, and then we'll convert these pixel measurements into micrometers. And just simple as that. On the other hand, for droplet generation under the dripping regime, we collect emulsion samples in a vial. Now, this was because the flow rates used for the continuous and the dispersed phase liquid were relatively higher. Therefore, the droplet generated, the size of droplet generated tend to be longer, and it will be too long for us to measure directly using the V++ demo. So as you can see here, this is an image of the bubble sizes generated, these are the emulsion sample of bubble generated under the dripping regime, collected in the vial. So we then measure the length of droplet using the following relationship equation, whereby this volume of sphere is taken to be the same as the volume of this droplet, which is regarded as a cylinder with two hemispheres N. And with all these parameters held constant, we can find the length of droplet L. So another reason why this approach was used was because that the image captured during droplet breakup is not quite clear, as you can see on our picture here. So instead we use this approach instead. Yeah. Moving on, I shall be discussing about the results obtained from our experiment. On this slide, you can see homogeneity in sizes of bubbles formed under the squeezing regime. This is because the flow rates used for continuous and dispersed phase liquid were quite slow. So the bubbles created in emulsions was more stable. So on this next slide, bubbles created under the dripping regime. You can see polydispersity of sizes because higher flow rates were used, which which contributed in coalescence of bubbles. So one size tend to be bigger than another. We have this graph here shows the dimensionless length of droplet with against the ratio of dispersed phase liquid against continuous phase liquid. As can be seen on this graph, we have a straight line relationship between the dimensionless length and the ratio of flow rates, which is in agreement with the proposed scaling equation before. Having said that, an increase in the flow rates of liquid will definitely lead to an increase in the dimensionless length of droplet. Of course, having all geometries of the channel constant. Now, this here is a comparison of the experimental results with theoretical estimation obtained from the proposed scaling equation. Now, of course, we use the alpha constant of 1, as seen on the blue equation here. So, as you can see, this graph it's pretty much the same, so it's an agreement. This here is the same graph, but then it is the droplet generation under the dripping regime. So it is on a logarithmic scale because it does not correspond to the linear relationship of the scaling equation. So from our experiment, we developed a new scaling model, shown here, this one here with the logarithmic term right here. So that's pretty much it. And finally, we studied the effect of viscosity changes in water, which is also the dispersed phase liquid, on the sizes of droplet generated. Now, as mentioned previously, the scaling equation is independent on the viscosity of the liquid used. So, as you can see, the statement was deemed as valid because there are two straight lines with little discrepancies on the green one here due to several errors. And we held the flow rate of oil constant, changing the flow rate of water. This is under the squeezing regime, remember. And results showed that an increase in viscosity leads to no changes in the dimensionless length of droplet. That pretty much concludes our experiment. So we have came to a conclusion that under the squeezing regime, Laplace pressure balance between two immersible liquids prevails over the cross-flow shear stress. And also the scaling equation proposed earlier was only valid for the squeezing regime and not the dripping regime for droplet generation. Instead, we generated a new model, as mentioned previously, for droplet size estimation under the dripping regime. And lastly, the scaling equation proposed for the squeezing regime is independent of the viscosity of liquid. In a nutshell, droplet generation under the squeezing regime tends to create more stable emulsions. We came across several limitations during the course of our experiment. Now, of course, then again, we came up with several recommendations to overcome such issues. Due to time constraints, we did not change the syringes used under the same day of experimental conduct. So there tends to be swelling of syringes due to minor vibrations of the pump. So this of course is to change syringes frequently, and without that, that might cause any deviations in flow rates, which will cause inconsistency in results. Another issue besides that, we have the droplets generated were unclear for the droplets generated under the dripping regime. This was maybe due to limitations of light, or maybe the image resolution of the camera was not high enough. So to overcome that, we can use a high-speed camera with high megapixels to provide slow motion analysis, and this of course can provide images with better clarity. Lastly, we can also study the effect of viscosity on scaling relation under the dripping mechanism of droplet formation. So with that, we can further justify that scaling law has no relation with droplets generation under dripping regime. And that pretty much concludes my presentation for today. Thank you for your attention, and if you may, feel free to ask me any questions. Thank you.